So let us start this unit on angle modulation, and in angle modulation we will be primarily learning phase modulation as well as frequency modulation, although these are only two possible kind of modulations in infinite possibilities which are covered under angle modulation. So we will cover this complete topic with programming also. So the programming can be done in MATLAB as well as in Octave. So the codes for both will remain the same. So let us first discuss what we mean by angle modulation. So, and let us also compare it with your amplitude modulation. So amplitude modulation to begin with was a linear modulation. By linear modulation, we mean that it is uh, it is of course using the superposition theorem. Means superposition theorem is applicable there, and that is why Fourier analysis or Fourier transformations can be applied directly there. So if you want to see the frequency domain behavior of any modulated waveform, you could directly use the Fourier analysis. However, this angle modulation is not linear in nature, it is exponential in nature, and for exponential kind of modulations we cannot use the Fourier analysis directly. So to see the frequency domain behavior of this modulation, whether it is phase or frequency or anything other than that which is not linear, we cannot directly use the Fourier analysis. We have to use something else. So we will talk about it later. But the aim of this lecture today is we will be introduced to the idea of instantaneous frequency instead of frequency. Earlier we were talking about frequency. Now we will be introduced to the idea of instantaneous frequency. We will learn the mathematics behind phase modulation and frequency modulation, and we will also see the case of general angle modulation, right? So in this video we are only going to see the mathematical aspect of these modulations and some coding related to that, so that we can see some waveforms etc in either MATLAB or Octave. So uh, rest practical things will be discussed in other videos, where we will also discuss the generation of phase modulation or frequency modulation and demodulation of these modulated waveforms and the constraints of noise etc on the channel, then how signal to noise ratio is affected by bandwidth and frequency usage etc. So this is just an introduction video. So now let us begin with this signal phi t is equal to a cos theta t, right? We are acquainted with this notation phi t is equal to a cos omega ct plus theta naught, right? We have used this signal many times in amplitude modulation, and we know that here this omega ct plus theta naught is a linear function of t. So whatever is written inside this cos argument here is linear in nature, and this omega c is a fixed frequency and this theta naught is some initial phase. Now there could be cases where this omega ct plus theta, that is this complete angle which is written inside this cos, is in general not linearly dependent on time. So we are taking this notation now theta t, and here we are assuming that theta t is in general not linear. It could have any particular form. So in that case, how do we define frequency and how do we deal with these situations? Because it's not always the case that cos will be this nicely behaved. So this is a generalization, and here we are assuming that theta t is any linear or nonlinear function of time. So now there the concept of frequency won't be used. We are going to introduce a new term now which is called as instantaneous frequency. So when we talk about functions which are general functions of time, which could be linear or non-linear, then we do not talk about frequency, we talk about instantaneous frequency. And for a signal which has linear dependence on time in terms of omega ct plus theta, linear frequency, instantaneous frequency and frequency will be the same. So for a general signal, the instantaneous frequency omega it is defined as derivative of this complete angle. Derivative of this complete angle will be the instantaneous frequency, not the frequency of the signal, right? It is the frequency at the instant t. So you can substitute any value here t, and you can get the value of frequency at that particular instant. This also suggests that this phi t signal at various different times will have different frequencies, And we will see that's what we mean by frequency modulation or phase modulation or angle modulation in general. So that is why we have defined this new term instantaneous frequency for a general class of cosine signals, right? Now obviously if you perform, if you want to get this theta t, you simply have to integrate this omega it from minus infinite to t, and omega I, instead of t we are using alpha because t is also in limit. So this is how you can get theta back, right? And a general assumption here is that at point minus infinite, things are zero in integrations that we will frequently encounter, because some authors use zero in place of t, zero in place of this minus infinite here. So it's just a matter of convention. We will stick with this convention that at infinite, whatever we have the value of this integral, it will be zero. So this is about the instantaneous frequency, and this is the angle. So if you have instantaneous frequency, you can get angle, and if you have angle, you can get the instantaneous frequency by just differentiating. So this is how we have introduced this instantaneous frequency. Now let's come to phase modulation, right? Now phase modulation is the kind of modulation in which this complete angle that you see here, theta t, it will vary as a function of message signal mt. So here you see this theta t is some omega ct plus theta naught plus kp into mt. This omega ct plus theta naught, as you see here, is a general linear kind of time dependent term. Omega c is fixed here, t is t, which is time, and for without losing generality, we can assume this theta naught to be zero. And this is how this complete theta t depends upon message signal. So this kp is some constant of proportionality, p because we are learning phase modulation. So kp into mt, right? So this is how your angle is defined. Now the phase modulated wave 5 pmt will be a cos omega ct plus kp into mt. So this complete angle, as you see, is not linear, because it's not linearly dependent on time, because you see here we do not know anything about mt, how message signal will be. It could be discontinuous at some point of time also, it could show some non-linear dependence on time also. So it all depends on mt, right? However, if we want to see how frequency behaves, so we take this complete angle and differentiate it with respect to time. So for phase modulation, the instantaneous frequency is d theta over dt, and this is omega c plus kp into derivative of this message signal, right? So we have just differentiated this thing and we have got the instantaneous frequency of this signal. So you see here there is some constant component which is omega c, and there is some variable component in frequency at every instant t. Means frequency at every instant t will be totally determined from this message signal only, because otherwise these terms are constant, omega c and kp. So it will be determined by derivative of the message signal, right? So this is what we mean by phase modulation mathematically. We will deal with more practical aspects in the coming video lectures, but this is how phase modulation is defined mathematically. Similarly, mathematically we can say that frequency modulation is a modulation in which the instantaneous frequency, not the frequency, in which the instantaneous frequency of this particular signal, generalized cosine function, will vary with respect to message signal. So instantaneous frequency, it varies with respect to this message signal, and the constant that we have taken here is kf, f for frequency modulation. It is actually instantaneous frequency modulation, right? So this is instantaneous frequency. If you want to get the complete angle, you have to integrate it from minus infinity to t, and this complete thing will be integrated and you will obtain this equation. So we can write the equation of frequency modulated waveform in time domain as a cos and this complete angle here. Here you see that there is an integral term, and we need to integrate this message function or from minus infinity to t, and then we have got this particular thing. So this is how a frequency modulated waveform in time domain is defined mathematically, right? We will come to the practical aspects of what is the meaning of this kf and what values should we use for kf, but we will see that through experiments on MATLAB or Octave, right? Now one important point to note here is, if I have a frequency modulator, obviously I can do frequency modulation. If I have a hardware device which is specially made for frequency modulation, of course I can do the frequency modulation, but the same thing can be used for phase modulation also, right? Or the reverse is also true. If I have a device for phase modulation, it can do phase modulation as well as it can be used for frequency modulation. How? If you look at the equation of these two, phi PMT and phi FMT. So if in place of MT, right, had it been integration of MT here, had it been integration of MT here, then this equation will resemble this particular equation, right? So instead of supplying MT as message signal in phase modulator, if I supply a integrated version of my input message, then this equation will be same as the frequency modulation. That's what we have represented here. If you take message signal, integrate it, and then supply it to the phase modulator, you will get the frequency modulated waveform. That means frequency modulated waveform is actually phase modulation for the integrated message signal, integrated input message signal. And this is also true for frequency modulators. If you have frequency modulator and you want to get phase modulation out of it, instead of supplying the input as MT, you supply it as derivative of MT. So you have differentiated your message signal. So let's have a look at phi PMT in this particular thing. That is, here you have got this FM. In this equation of FM, let's see, if in place of this M alpha you have derivative of M alpha, then integration of derivative will become the function itself, and you will see that this equation will be exactly same as this equation. Only the difference will be between Kp and Kf. Anyway, they are constants, right? So it is clear that even if we have one kind of modulator, the other kind of modulation can be done, right? So phase and frequency modulation, their waveforms will also not be visibly very different, because something which is seen as phase modulation by some people can be seen as frequency modulation by other people, and this is in general true for any general angle modulated wave. So instead of restricting ourselves to phase and frequency modulation, let us not talk about the general angle modulation case. In that case, we assume that phi exponentially modulated, EM means exponentially modulated wave, it can be written as A cos omega ct plus psi t. So here this psi t, in case of your phase modulation, you see here the angle that you had derived was this. So psi t was Kp into Mt for phase modulation, and if you see theta t here, the solved form is this. So theta t omega ct plus this part was psi t. So this psi t could be any function of time. So if it so happens that it is this, then it becomes frequency modulation, or otherwise it becomes phase modulation. So psi t could be any function. It could be, a linear time invariant system or other systems also. But let us now take out of the infinite possibilities only linear time invariant system, because we know the properties of linear time invariant systems, and we can deal with that mathematically. So if we take an input signal MT and we pass it through some linear time invariant system with frequency domain responses Hs, so its impulse response will be small ht, and after passing it through this, the response psi t can be written as m alpha ht minus alpha d alpha. So this is just the convolution between mt and the impulse response ht. So here the signal will be convolved. We all know this from our signals and systems course. And if this is passed through 1 by hs filter, we will get back our mt. So we are using psi t as this particular function, right? So if we want to use a LTI system, then psi t, if we treat it as this, the equation becomes this. Phi exponential modulation will be this particular form. And this is valid for LTI system with impulse response ht. Now, if you substitute ht is equal to kp into delta t, that is, if you substitute this particular term by this particular term, then you will get phase modulation. You can verify it for this self. You will get this particular equation here. Similarly, for ht is equal to kf into mu t, that is unit step function, you will get frequency modulated waveform. So you can verify it by substituting here. So this is what we mean by general angle modulation, right? So in this slide, we have only covered the mathematical aspect of how we deal with these kind of things mathematically, and we will talk about practical aspects in the coming video lectures. But let us now see some programming and how can we plot the waveforms which are either phase modulated or frequency modulated. So for that, if you are not aware of MATLAB or Octave, you need to have some basics of MATLAB and Octave, and you need to download either MATLAB software, which is it is a paid software, so you need to purchase the license, or otherwise for our purposes there is another software which is called as GNU Octave. So it is free of cost and you can use it for any purpose. So GNU Octave, you type on Google, and on the first link, if you will click, the website for that will open, and here in the download tab you can just go and download that software. I'm using Windows operating system, so you can go to the Windows version, and here if you see, you have various versions of installer. I prefer to use this one because it's a zip file, it contains everything. It is the largest file out of these three. So I am using this file. You just have to download this file and you don't have to install it because it is a zip file already. So after this, what will happen is you can unzip that file and unpack it into a folder by using any open source software like 7-zip or WinZip, and then this folder will be there. Inside that folder there are various files. We do not need to disturb them, and when you run Octave for the first time, you will just double click this thing, Octave first time VBS, and let the Octave software open, so it will auto configure itself. And from the next time when you will run it, you have to press this thing, octave.vbs, right? So you can preferably make a shortcut of this on your desktop after you run it for the first time, and when you will open Octave, it will look something like this, right? So it has various windows. It is similar to MATLAB software if you use that in your college, etc. So this is your MATLAB like interface where you have this file browser, then you have workspace, and you have this command history, etc. And this is your command window. So this is command window, and if you want to go to editor, this is your editor. So this is editor, and here you can write your code. I have already pre-written some code, we will discuss that, but this is just a short introduction to how to install Octave, etc. And then again, if you're not aware of MATLAB programming, so I suggest you to start with any good book, or in case you want to read it from my channel, you can go to my channel, and in the playlist tab, you will see this playlist on image processing using GNU Octave. You can click on that, and the videos for our usage will be this video number 2, which will tell you basics of Octave. And this, you can also see this video because here you will know some basics about plotting. But I assume that you already know MATLAB, and hence you also know Octave. MATLAB and Octave, they do not have any difference. You can run the code without any major change on both of these softwares interchangeably, right? So now let us discuss this frequency modulation first. So the code is already written here, and we will discuss it line by line. And we will, first of all, let us see the output of this particular code. How does the output look like? So this is what we want to achieve. This is our message signal. So I have taken a sinusoidal signal as our message signal, and it is not actually a sine signal, it's a cos signal. So we have taken this signal as our message signal, and this is the carrier signal. Now carrier signal has to be of high frequency as compared to the message signal, right? So this is carrier, this is message, and now we are going to frequency modulate them. So you see here you have got a frequency modulated version of this. Here you see the amplitude of this message signal is high, so correspondingly is in this region your frequency of the signal is high, and here you can see that the amplitude of your message signal is low. So in this particular region you can see that this amplitude has also become low. Not the amplitude, but the frequency has become low in this particular region. So this is what we mean by frequency modulated signal, and let us see the code for that. So although we are reading this subject on analog modulation or analog communication, but then again in MATLAB, if you want to plot something, you have to discretize things first, because continuous variables, they are dealt in MATLAB, but then it's very involved. So we are just first discretizing the signals by using sampling theorem. So these close all, clear all, and CLC are conventionally written before any file opens, if it is not a function file. And then first of all, let us decide the signal construction on the basis of sampling theorem. So the lines that you see here, 6, 7, 8, and 9, they are written for using the sampling theorem, because I'm treating the continuous signals, but inside MATLAB they will be treated as discrete signals. So I'm using proper sampling theorem so that reconstruction of these signals is properly possible. So I'm assuming that you know what sampling theorem is. So I have selected my sampling frequency as 1000, which means that I will be able to plot correctly up to 500. That is from minus 500 to 500. It will be 1000 total samples will be there. So sampling frequency is minus 1000, and the time gap between two consecutive samples will be 1 by fs. So this is my time gap between two consecutive samples in time domain, and I'm assuming my length of signal is 500 samples, right? You could increase it or decrease it also, but 500 is a good enough number. And then the time axis is constructed in this way. I'm going from minus L by 2 till L by 2 into t. T is multiplied because there is a gap of capital T, which is 1 by fs between two consecutive samples, and I have started from minus L by 2 to L by 2. And floor, because this L by 2 could also be a fractional number, so I have taken this floor function. So floor function will take it to the lowest integer. So if it is 8.9, it will make it 8. If it is 8.1, it will make it 8. Similarly, there is a ceiling function also which you can use. So it will bring any fraction to the nearest greatest integer, right? So this is how you have defined your time axis as per the sampling theorem. Now we want to make our message signal. So message signal will be cos of 2 pi 20t. So the 20 is the frequency of my message signal, and t is the time axis that you have just constructed by taking proper sampling theorem into account. By sampling theorem, we mean that we need to take twice the sampling frequency should be twice as compared to the maximum frequency of your signal. So here the carrier signal is having a frequency of 100, so the sampling frequency should be at least 200, but we have taken it to be 1000, and that's way more than what we need theoretically. So it's a good practice to keep sampling frequency high. So now message signal and carrier signal have been designed, and now I am deciding a value of kf as 250. We will discuss more about it, how to choose the value of kf, but for the time being, let's take some kf value. And what do we mean by this kf? This kf is something that we have just seen here. If you're talking about frequency modulation, this is kf. This is the constant that we have taken for frequency modulation. And then now let's write the equation for modulated signal. So the modulated signal has this particular equation. So I'm just zooming this portion. Let's see. So this was our equation. It has to be a cos omega ct plus kf into integration of the signal mt from minus infinite to t, right? So we are writing here, I am assuming the value of A as 1, because anyway the signal amplitude is taken as 1, and it is irrelevant in frequency modulation because amplitude will not be tampered in frequency modulation. So now cos of this omega ct, omega is 2 pi into frequency into t. So this was your carrier signal, this frequency is 100, so this is cos 2 pi ft, that portion, plus kf. This is kf, and this particular thing t into cumulative trapezoidal integration of message signal, this particular portion which is highlighted in blue, it implements this particular thing, kf integration from minus infinite to t m alpha d alpha. Now this cumulative trapezoidal integration will integrate whatever is written inside it, assuming that the gap between the consecutive samples is 1 unit. However, the gap between our consecutive samples is not 1 unit, it is capital T. So if there is any other gap, you have to multiply that gap before this command, and this command will internally readjust the cumulative trapezoidal integration such that the interval between two consecutive samples is capital T. So this is how your frequency modulation will be done, and the results will be stored in modulated signal. And you already know how to plot figures in MATLAB. So figure is plotted here, and the main command through which you have plotted various signals is plot T into message signal. Rest of the arrangement is made to bring 3 tiles on your final figure window. So if you see it here, this is how your plot should look like. So this is 1 tile, 2nd tile, 3rd tile. So it is done through this subplot function. If you're already not aware of these things, you can go to the basic MATLAB video and see it there. So similarly, we have plotted these 3 functions. So all these 3 functions are here, right? So this is how frequency modulation is accomplished. If you have done frequency modulation, phase modulation is also easy. So this is the code for phase modulation. Again, the same sampling theorem is being used here to create the time axis. After that, you have made this equation of modulated signal as cos 2 pi ft, that is omega ct into kp, and message signal. So if you have a look at again the equation of this phase modulation, I'll zoom it. So this was the equation here, a cos omega ct plus kp into mt. So that's what we are implementing here. So this is cos of omega ct up till this point, and then kp into message signal, right? So then the rest of the thing is plotting, and if you run this particular code, you will be able to see that this is the phase modulated signal, and you could hardly figure out that whether it is frequency modulated or phase modulated. So these signals look same. Whatever angle modulation is used, the signals will have same kind of representation in time domain after modulation, so you cannot figure out which signal is which signal, right? Similarly, if you want to implement it for the general case, that is general angle modulation, this is the code. And here again, this time axis is generated by taking proper sampling theorem. Then you have generated the message and carrier signals as usual. Then now you have created this LTI system for phase modulation first. So you could use many LTI systems, but we have taken this LTI system as first of all the impulse function, right? Why impulse function? Because we want to implement this particular equation, the equation which I had shown here. If you take ht as kp into delta t, that is impulse function weighted by something, then your generalized angle modulation will become phase modulation. So with this minor change, that is ht1 is the first impulse response that you are using. So it is all zeros for the length of this t. So whatever is the length of this t, you have all zeros, and you have replaced the central element by kp into 1, so that it becomes, this combined thing becomes an impulse function. And then you have applied this, and you could also use ht2 as a unit step function. So this is the code for that. You can figure it out for yourself, that this will create a unit step function, and you can get the results accordingly. So while plotting, you have a choice to make your ht as either ht1 or ht2. So I have selected ht1, and we will get the plot of this particular function for phase modulation. Now the equation for generalized modulation is written here, cos 2 pi omega ct into t cumulative trapezoidal integration. This trapezoidal integration is one such integration. You could use any one of them. You can type help cumulative trapezoidal integration, and you will also get various other integrations in the suggestions. So we have to perform convolution. So for that, the convolution command is this, and between message signal ht and same, because you want to keep the length of this modulated signal same as that of message signal. So this equation is here. If you see, this general equation is this equation which we have implemented, and after implementing this, you can see the results. So I'm just running this code, and these are the results. So again, the results look very indifferent from what we have earlier done. So this is how you can see the waveforms in time domain. Side by side, I should also have plotted the frequency domain representations of these, but it's not very easy here, because as we said earlier, this modulation is in general not a linear modulation, it is an exponential modulation. So Fourier analysis cannot be directly applied here. So we will talk about that more when we will use this when we will make calculations on bandwidth, etc., for FM and its various variants. So we will see it there. So this is it for today's lecture. We have just introduced mathematical notion of phase, frequency, and angle modulation in general. We have learned instantaneous frequency, and through some coding we have seen our results. So in the next video, we will elaborate on all these, and we will try to have some insights about this topic. So thank you for watching this.